Now, the last part of the sound lecture is about the Doppler effect. The Doppler effect has so many different applications in so many different areas of science. In meteorology, in weather, you can figure out how fast a storm is coming towards you and how far it is away. In astronomy, you can figure out how fast a star or galaxy is moving away from you or towards you. So many different applications, including that one we all love, the police officer who tells you that you were speeding. They use the Doppler effect with radar. We're going to just talk about the Doppler effect for sound for right now, but all the different types of Doppler effects are truly very fundamentally the same thing. So the Doppler effect is simply the change in perceived frequency due to motion of a wave source or wave observer. Either one of those will cause the Doppler effect. It does occur for both sound and light waves, electromagnetic radiation as well. Now, it's very important to understand here, we might hear some changes in volume, but that is not due to the Doppler effect. That's just due to something being closer or farther. That is more like an inverse square law. That's not the Doppler effect. The increase in amplitude, something totally different. Doppler effect is a change in frequency. For sound, we'll hear that as a change in pitch. Now, I've got a couple of demos here of some sounds, and let's take a listen first. And I want you to listen for how the pitch changes with this siren. Approaching. Departing. Now, hopefully you were able to hear how the pitch went down when it was departing. Now, yes, it got louder as it got closer and softer as it got farther away. That's not what we're talking about. We're talking about the pitch. It goes a lower pitch as it goes away. And we'll also hear this for a sports car. Let's check out the sports car. Similar kind of effect. The pitch goes down when it's going away. So as it approaches, the pitch is higher than normal. And then as depart, the pitch gets lower. Here's another great demo with a Doppler ball. And with it moving faster, so this is the Doppler effect. And now let's actually explain this using this awesome demonstration. What we have in the middle of this screen here is a jet, and it's giving off sound waves. Now, what do you suppose those lines represent? Well, those lines represent the compressions of the wave. And this is actually a spherical wave. It's going in all directions. It's going out in all directions, everywhere. Spherical, we're just looking at one plane of them. And it is, so it looks like circles. Like if you dropped a pebble into a pond, something like that. So if these lines represent the compressions, what do these spaces in between represent? If you said rarefactions, you'd be right. Now, we're not seeing the Doppler effect in it right now. We're just seeing a sound wave. And what I want you to do is I want you to say now when I'm going to put my ear over here. This cursor is an ear. And I'm going to put the ear right here. I want you to say now when this wave, the compressions hit the ear. Like when your eardrum would go in, say now. So let's start it off again. Nothing hitting us yet. Now, 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 now. Those are when your eardrum would go in. This time what we're going to do is we are going to actually get this thing moving. We're going to get it moving in this direction at about a third of the speed of sound or so. And I want to do the same trick, say now, when your eardrum would go in. And I'm going to be waiting over here for this sound. Nothing yet. Haven't heard it yet. Here we go. Now, 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 now. Let's make it even more extreme. I'm going to go about 70% of the speed of sound. And here's our ear right here. When does our eardrum go in? Now, 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 now. Now, what is the difference there? When this thing is moving toward us, the frequency is higher. Here's the frequency when it's not moving. Now, 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 now. Make it move toward us, and the frequency becomes now, 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 now. It's faster frequency. We hear a higher note when the sound source is moving toward us. Now, what if the sound source was moving away from us? Let's do this again. I'm just going to start this again right here. This time we'll be behind it. Again, now, 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 now. But now I'm going to have this move away from us and say now when our eardrum goes in. Now, 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 now. Let's make it even go faster away from us. Now, 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 now. So when the source is moving away from us, we hear the frequency as lower. Now this time, let's try moving towards the sound source. Now this time the sound source is just staying still, but now my cursor right over here, we're going to move, we're going to first, again, just sit still. Now, 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 now. But then this time we're going to move toward it. Say now when we hear the compression makes our ear go in. Now, 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 now. So notice when we're moving towards this sound, the frequency goes up. Let's do the same thing, but moving away from it. Now, 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 now. So we see when the observer is moving away from the sound, we also get a lower frequency. With the source at rest, the cursor is the observer. You get now, 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 now. When the observer moves towards the source, that becomes now, 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 now. In other words, we're just moving the frequency goes higher. There is a difference, though. What is the difference between the moving source case and the moving observer case? In which one of those does the wavelength actually change? Let's look back at that one more time. In which one does the wavelength actually change? Notice that in the moving source case, the wavelength does get shorter or longer. The distance between the compressions actually changes. So in the moving source case, the wavelength actually changes. And that causes the frequency to change of your eardrum going in. In the moving observer case, only the frequency of the eardrum changes. The wavelength doesn't change. So if you measured that wavelength for the moving observer case, it would still be the same distance between those wave fronts, between the compressions. It's just that we're moving into them, heading towards them, or heading away from them, as the case may be, such that our eardrums go in at a lower or higher frequency. It'll go in at a higher frequency if we're moving towards the wave fronts. It'll go in at a lower frequency if we're moving away from the wave fronts. Although in the moving observer case, the wavelength really doesn't change.